Have you ever wondered why a tiny little glitch somewhere can bring down an entire website? A total system meltdown. Today, we're going to pull back the curtain on why these complex digital systems fail and talk about the really clever safety switches that engineers use to stop a disaster before it starts. Let's dive in.
I mean, we've all been there, right? You're just about to check out, you're buying those concert tickets, and boom, the whole site just dies. So how on earth can one small hiccup, maybe a problem with the payment service, cause the entire thing to shut down?
Well, that phenomenon actually has a name, and it's kind of the villain of our story today. It's called a cascading failure. You can think of it like a chain reaction, where one small, isolated problem starts spreading, and it just knocks over other services one by one until the entire system collapses. To really get this, you have to understand that modern websites and apps aren't just one big program anymore. Nope, they're actually a whole network of tiny, specialized services that are all constantly talking to each other. Now, this is super powerful, but it also creates the perfect setup for, you guessed it, a digital domino effect. So here's how it plays out. Let's say the service that handles user profiles fails. Well, the recommendation service, which needs those profiles to work, it goes down too. And then the homepage, which needs to show you those recommendations, well, it fails next. It is literally a chain reaction, a cascade of failure, just like a line of dominoes falling.
Okay, so how in the world do we stop these dominoes from falling? Well, engineers use this really clever design pattern that was inspired by something you almost certainly have in your own home. Let's just call it a software safety switch. I want you to think about the circuit breaker in your house's electrical panel. Its job is to detect a dangerous electrical surge and just cut the power to prevent damage, maybe even a fire. A software circuit breaker does the exact same thing, but for data. When it detects that a service is failing, it cuts off the requests going to it, preventing a system-wide meltdown.
So let's get into the details. How does this software electrician of ours know when it's time to flip the switch? It's actually a pretty simple three-state process.
So it all starts in the closed state. Think of this as the power being on. Everything's running smoothly and requests are flowing just fine. But if too many of those requests start to fail, bam, the breaker trips and we move to the open state. This is our electrician cutting the power. All traffic to that failing service is stopped, giving it some crucial breathing room to recover. Then, after a little bit, we move to the half-open state. Our electrician cautiously tests just one little appliance. A few test requests are sent through. If they work, great, the breaker closes and we're back to normal. But if they fail, nope, it's right back to the open state to protect the system.
And this isn't just some neat idea on paper. Research has shown that putting this pattern into practice can slash those cascading failures by over 83%. I mean, that is the difference between a tiny little hiccup and a full-blown catastrophic outage.
Okay, so the circuit breaker did its job beautifully. The failing service got the time it needed to recover. So we're safe now, right? Well, not quite. The act of recovery itself can actually create a brand new and much more subtle problem. It's called a thundering herd. Just imagine every single user, every single system that was waiting for that service to come back online tries to reconnect at the exact same millisecond. It's chaos. It's like an entire stadium full of people trying to cram through one tiny little door all at once. This synchronized rush creates what we call a retry storm. It's basically an unintentional, self-inflicted denial of service attack. It immediately overwhelms the service that just recovered, causing it to crash all over again. You get stuck in this vicious cycle. So, how do you solve a stampede? You can't just tell thousands of computers to, form an orderly queue. The solution is actually surprisingly simple, and frankly, it's elegant. You introduce just a little bit of controlled chaos. See, the problem here is synchronization. It's everybody trying to do the exact same thing at the exact same time. So, to solve it, we just need to break that perfect timing. We have to make their actions just a little less predictable. And that strategy is called Jitter. It's so simple, it's brilliant. Instead of every client retrying after, say, exactly 5 seconds, you tell them to wait about 5 seconds. So one might wait 4.9 seconds, another might wait 5.2. This tiny, tiny bit of randomness is all it takes to spread out the requests and prevent that stampede. If you just use a fixed retry schedule, you're basically asking for a disaster. Even a smarter approach, like what we call exponential backoff, can still create these synchronized waves of traffic.
But when you add jitter to that backoff, the retries are smoothed out into a much more gentle, manageable flow. And the difference is just dramatic. Look at this. Without jitter, you get this massive, dangerous spike of traffic that can easily knock a service over. But with jitter, that exact same amount of traffic becomes this gentle, manageable flow that a recovering service can actually handle.
So we have our two key tools in our toolkit: the circuit breaker, which isolates the initial failure, and jitter, which helps manage the recovery. So how do these actually work together in a real-world system?
Well, it really boils down to just a few key steps. First, you wrap any risky call to an external service inside a circuit breaker. Second, you decide on your failure thresholds. How many failures are too many. Third, you've got to have a fallback plan for when that breaker is open. Maybe you show some cache data or a friendly error message. And finally, and this is absolutely crucial, you make sure that any and all retry attempts use jitter.
So what's the big takeaway here? It's that you just can't prevent every single failure. It's impossible. The real goal is to build systems that can survive them gracefully. The circuit breaker contains the initial damage, and jitter makes sure that the recovery process doesn't accidentally trigger a brand new crisis.
Look, at the end of the day, every complex system is going to face failure. That's a given. So the real choice engineers have to make isn't if systems will fail, but how. Will they be brittle and just collapse like a line of dominoes? Or will they be resilient with the built-in intelligence to isolate problems and ultimately heal themselves?